Okay, everyone. Thank you for joining our UNIFI seminar series today. We have a great talk from Wei Du. He is a researcher at the Pacific Northwest National Laboratory. He is a principal investigator for a number of DOE projects that are focused on how high penetration of inverter-based resources will be integrated into the grid. And then also he's leading our modeling and simulation area inside the UNIFI consortium itself. So he's been doing quite a bit of work understanding transient and dynamic behaviors of electric power systems. I'm not sure why that screen popped up, but maybe we can switch back to Wei's screen. Maybe you want to take over Wei on your screen.
So it looks like, Ben, I cannot share a screen. It says
you cannot share the screen?
Other
Okay.
participant is sharing now.
Okay. Let's try it over.
Maybe
try
now,
again.
now
Try
I can
now.
share. Yeah. Okay, so can you see my screen now?
Yep, we can see your screen now. Although now it's in the double mode. Yep, now it's in the right mode. Okay.
Great. So thank you very much, Ben, for the introduction. So hello, everyone. So I'm Wei Du from Pacific Northwest National Laboratory. So first of all, I'd like to say Happy Lunar New Year to everyone, especially for those who are supposed to take a vacation but decided to listen to my presentation today. Thank you, and hopefully I will not disappoint you. So today's presentation is about transient dynamic modeling of Droop-controlled grid-forming inverters at scale. So it will be a journey from a single microgrid to an integrated transmission distribution system with 10,000 inverters. So here is the outline. So firstly, I will talk about the survivability of autonomous microgrids during overload events. So it's mainly about how the third microgrid deals with these overload events. And for the second section, I will talk about the comparison of two widely used grid-forming Droop controls. So for this section, I really want to provide an insight into the different dynamic responses of the single and multi-loop Droop controls. Hopefully that can be helpful to better understand grid-forming control. And for the third section, I will talk about the modeling and the simulation of an integrated transmission and distribution system with 10,000 inverters. So I will mainly talk about how we set up this transmission distribution system co-simulation platform using the DOE invested open source tools, and then share some preliminary study results of this TND system with 10,000 grid forming and grid following inverters. And finally, I will share some final thoughts and introduce the future work. Okay, so here is the first section, the survivability of autonomous microgrids during overload events. Firstly, I'd like to review the basic concept of grid forming and the grid following. So today, most grid connect inverters actually use this voltage source inverter, but different control strategies make their dynamic response totally different. So there are typically two types of controls, the grid following and the grid forming. So at the left side is grid following concept. So today, maybe more than 99.9% grid connected inverters use this grid following control. So basically, the idea is that they make this a voltage sourced inverter approximately behave as a current source. So they directly regulate the current of this inverter inject to the grid. So typically they can use a phasor lock loop and the current control loop to do that. So the advantage of this grid following control is that it's easier to regulate the current, so it's easier to control the P and the Q of this inverter inject to the system. However, the disadvantage is that these grid following inverters do not directly control the voltage and the frequency. And typically they cannot work without a grid. Okay, so that's the grid following concept. And for the grid forming, at the right side, typically they make this voltage source inverter approximately behave as a voltage source behind an impedance. So the advantage of this grid forming control is that it's directly control the voltage and frequency. So it can provide fast voltage and frequency control of the system. And also it can work in islanded system. So that's why it matters for microgrid. But also because it does not control the current directly, so it might have some overcurrent issues or overload issues. So to summarize that, so I would say for grid following inverter, at the beginning of a disturbance, the inverter output current is approximately constant. And then there might be some external controls to adjust the current reference. But for grid forming, I would say that at the beginning of the disturbance, the inverter internal voltage is approximately constant. And then there are some external controls to adjust the voltage magnitude and phase angle, such as Droop control. Okay, so after introducing the grid forming concept here, I would like to briefly review this Droop control concept. So as I mentioned, the grid forming inverter is a voltage behave as a voltage source behind impedance. So it's not just a voltage source, it's a voltage source behind impedance. And this impedance, or say coupling reactance, actually is very important for the controller design. Now, if this XL is well designed, so from these classic equations, we can see that this active power P is approximately linear with this phase angle delta P. And the reactive power is approximately linear with this inverter internal voltage E. In that way, we can regulate P by controlling the phase angle and the regulating Q by controlling the inverter internal voltage. So based on this well-designed coupling reactance, so we can use Droop control to parallel multiple voltage sources in the system. So for example, this power versus frequency Droop control makes sure that when we have multiple voltage sources in a system, their phase angle remain synchronized. We do not use phase lock loop. We use this PF Droop control to make sure their phase angles are synchronized. So this is actually a very simple negative feedback control. So let's take a look at this equation. P is approximately linear with this phase angle. Let's consider this voltage source connect to the grid infinite bus through an impedance. So let's say if any small disturbance cause this phase angle delta P to increase, and then because of this equation, this active power P increase. But because of this Droop control, the controller reduced its frequency omega. And by reducing this frequency omega, because this phase angle is the integration of this omega, so the phase angle decreased. So from this control loop, we can see that if any disturbance causes this phase angle to increase, this PF Droop control actually prevents the phase angle from further increasing. So this is actually a very simple negative feedback control that makes sure this system is small signal stable. So its phase angle is synchronized to the grid. And similarly, this QV Droop control just makes sure that when we have multiple voltage sources work together, they do not have circulating wires between them. Okay, so after reviewing the basic concept of grid forming and Droop control, here I like to talk about how the third microgrid deal with overload events. So this slide shows the third microgrid testbed. I think it's the first inverter-based microgrid in the world. It was founded by DOE, and the principal investigator is Professor Bob Lester from University of Wisconsin-Madison. I think this program probably runs for almost 20 years, and I was involved in this, fortunate to be involved in this program as a student. So I think the most important thing I learned from this third microgrid is actually how it deals with its overload events. Because the grid forming inverter behaved as a voltage source behind the impedance. However, it's not an infinite bus. We have to respect its own power limitation. So for example, when we work in the Droop control mode, what happens if this inverter reaches maximum output power? So we need to deal with that because that's a real operational issue need to be addressed. And I actually didn't see many other papers discussing about that. But for third microgrid, so here we proposed an Pmax and Pmin controller, I'll say the overload mitigation controller, to address this overload issue. So we can see here it's a very simple PI controller, which measures active power P and adjusts the frequency added on this power versus frequency Droop control. And it has two functions, two major functions. The first is, when you're microgrid, when some of the inverters are overloaded, so this controller can help to achieve overload transfer. And the second function is that, when some severe overload event happens, if all inverters are overloaded, this controller can help to achieve under frequency load shedding. Okay, so here I will use some very simple cases to explain how this controller works. And let's consider this very simple two inverter system. We have two grid forming inverters, A1 and A2, and we have loads here. And for this case, at the very beginning, we dispatch the output power of A1 to be near its maximum. As you can see here is a 60 kilowatt. However, the output power of A2 is far away from its maximum. So it's the green line here. So that is pretty normal, right? Because in the microgrid, you want to dispatch the output power of the generation units. So in this case, we dispatch the output power of A1 to be near its maximum. And in this case, if we switch this load 2 on, you can see what happened. Because both A1 and A2 are voltage sources, so they maintain their internal voltage to be constant. So the consequence for that is that they automatically increase output currents to meet this load change, L2, load 2. So in this case, we can see that both A1 and A2 increase their currents so that the output power of A1 exceeds its maximum because it was already at its maximum before this load switching. So in this case, we can see that after we switch this load 2 on, A1 is overloaded. So this overload will cause problems. If we have this A1, if we have a PV inverter connected behind it, its DC bus voltage will collapse. If this A1 has a maybe synchronous machine connected behind it, this synchronous machine will stall. So for this real operational issue, we really need to design some autonomous controller to address this issue in a very fast time manner. Okay, so for Surf microgrid, here we designed an overload mitigation controller to address this issue. As you can see here, in normal operation, the output of this controller is 0 because of this 0 saturation. However, once this output P exceeds its maximum, and this controller will be activated to quickly reduce the system frequency. Actually, by reducing the frequency of this inverter, it reduces its own phase angle relative to the second source. By changing the phase angle, actually, we change the power flow between them. So here is a results with that Pmax controller. You can see that for the same case, if we switch this load 2 on, we can see both A1 and A2 increase their currents to meet this load change, and then A1 is overloaded. However, once A1 becomes overloaded, its Pmax controller is activated to reduce the frequency rapidly. So we can see that during the transient, we can see the frequency of A1 actually drops faster than the frequency of A2. So there is a frequency difference between them during this transient. And this frequency difference actually results in the change of phase angle. And the change of phase angle actually redistributes the power flow between the two inverters. So we can see that after a short time frame, maybe 0.2 seconds, the output power of A1 goes back to its maximum, and the second source picks up the additional load. So this controller actually autonomously transfers this extra load to the second source. So this is how this controller works for the first function, overload transfer. So now, and also go back to this slide a little bit. And actually from this Droop curve, we can see that actually the Droop curve becomes vertical when this source is overloaded. Okay, so now let's talk about the second function. It's about under frequency load shedding. So for the first case, we talk about the case that when some of the inverters are overloaded, but some other inverters still have sufficient generation. But for some even more severe overload cases, the entire system, all the inverters can be overloaded. So for that case, we have to trip some additional load to let the system survive. So actually that controller can help to achieve under frequency load shedding for this microgrid. So here is a simple case. I just want to briefly explain how it works. So let's consider these three inverters, three grid forming sources in the system. And then we treat this energy storage as a severe contingency. And that results in the overload of both inverter grid forming inverter A1 and the synchronous machine B1. And actually, because of these severe overload events, the Pmax controllers for both of them are activated. So the system droop curve of the both sources become vertical. So that means the frequency can be driven down by this Pmax controller. And then we have a frequency relay installed at this load bank 4. Once the frequency drops to the load shedding frequency, this frequency relay detects this under frequency event and trips this load bank 4, and the system survives this severe overload events. So basically, the idea is that when all the inverters are overloaded, all inverters droop curves become vertical, so the system frequency is driven down. So it can help to trigger under frequency load shedding. So at the left side is actually what happened in the field, the third microgrid. It's when the energy storage is tripped, both inverters and both inverter and synchronous generators are overloaded. And after about 0.5 seconds, load bank 4 is tripped and the system survives. And the right side actually will show the electromagnetic transient simulation and also the phasor domain simulation. You can see they match very well with each other and also match very well with this field data. And here we plot the frequency. You can see how this frequency is driven down by that Pmax controller. And after the load has been tripped, the system survives these severe overload events. Okay, so another important finding is how we design the controller parameters. Now we design this Pmax controller, but how we design the controller gains. So actually, a very important finding for this study is we found a small signal stability boundary for this microgrid. What we found is that, as I mentioned, the coupling reactance is very important for the controller design or the system stability. What we find is that if we have a larger coupling reactance, we can have a larger controller gains to maintain the system stability. As you can see here, if we have larger coupling reactance, we can have larger gains to maintain the stability. So this is a very important finding for this work, and also it will be very useful for the next section. Okay, so after talking about how the microgrids survive the overload events, so here I like to jump into some details of some power electronics controls. So here I like to do a comparison of two widely used grid forming Droop controls, and hopefully that can be helpful to better understand the grid forming control. So in this section, in this presentation, we mainly talk about the Droop control. But in the power electronics world, even for Droop controls, there are so many different types of Droop controls in the literature. And when I was a student, I remember there are two very popular Droop controls as shown in the slide. So for the left side, it's I call it a single loop Droop control. It's basically just a third Droop control. And at the right side, I call it a multi-loop Droop control. It's also very popular in all kinds of literature. You can see these two controls look very similar because both of them have this Droop control, this power versus frequency Droop control, and this reactive power versus voltage Droop control. However, they are also quite different. For this single loop Droop control, it's just quite straightforward, just no inner loops. But for this multi-loop Droop control, it looks very much more advanced. It has Droop control, and it has voltage loop, and has the inner current loop, and here is the voltage and current loop. So they are also very different. So I noted the difference between them when I was a student, and I was quite curious about that. So I set up a simulation and want to compare the results, compare their dynamic performance. And I find that under some situations, I can easily tune the controller parameters to match the results. So in some situations, the dynamic response look very similar. However, in some other situations, no matter how I tune these controller parameters, the results just don't match. They look quite different. So I don't know what happened. I don't know why. So even when I got my PhD degree, I still don't understand the difference between them. So finally, I think I have some better understanding of these two controls when I was doing a postdoc after 2 years practice in industry. So for this section, I just want to share some understanding of these two controls, and hopefully it can be helpful to better understand grid forming control. So first, like take a quick look at of these two controls. The left side is a single loop Droop control. From the LCL filter, because I'm quite familiar with this control, I know that typically L1 is typically much smaller than L2 when we work on the third microgrid, because we know L2 will play as a major role for coupling reactance XL. And also, it does not have any inner control loops. And for the multi-loop Droop control, when I read from the literature, they also have the LCL filter, but typically L1 is much larger than L2. And in some literature, they even do not have L2, they only have this LC filter. And also they have this cascaded inner voltage and the current loops. Okay, so this observation probably doesn't help too much to understand that. So we need to go further to further understand it. So to do that, we need to revisit the fundamental concept of grid forming inverter. So as I mentioned, the grid forming inverter is actually a voltage source behind the impedance. So we need to analyze for these two controllers, where does the controller control the voltage magnitude? Where does the controller control the frequency or phase angle? And where is the equivalent coupling reactance? So with these questions, let's further analyze these two controllers. As you can see here, for this single loop Droop control, for this power PF Droop control, when this power increase, it reduces the frequency, right? And then the integration of this frequency is the phase angle. So it's a phase angle, but this is a phase angle of this modulation waveform. So that means when the P increase, it directly reduces the phase angle of this modulation waveform. So this is the phase angle of this inverter internal voltage here. And for this QV Droop control, it measures the terminal voltage and controls the magnitude of the terminal voltage with this QV Droop control. But it's controlled that through an integrator controller by directly increasing or decreasing the magnitude of this modulation waveform. That means it's directly controls the magnitude of this inverter internal voltage. So based on this analysis, so we can see that this Droop control actually directly controls the phase angle and the magnitude of this inverter internal voltage, or say modulation waveform. So that means in the fundamental frequency, at the fundamental frequency, this inverter can be equivalent as a voltage source behind the impedance L1 and L2, because it directly controls the phase angle and the magnitude of this inverter internal voltage. So both L1 and L2 can be considered as its coupling reactance. And this filter capacitor can be ignored because of its small value in the fundamental frequency. So this circuit behave as a voltage source behind XL1 and XL2. And for this multi-loop Droop control, so what it does, you can see there it has 3 loops, right? The Droop control loop, voltage loop, and current loop. But we need to understand that maybe in this way, because if we have the voltage loop and the current loop, actually these loops are designed to have a very high bandwidth. So what it does is that actually that it controls the capacitor voltage here, VO, and this voltage and the current loops make this filter capacitor voltage as an ideal voltage source through these fast control loops here. And what this Droop controller did is that when the P increase, it reduced the phase angle here, theta, but this phase angle is actually the phase angle of this filter capacitor voltage. So it actually, when the P increase, it reduced the phase angle of this filter capacitor voltage. And for the QV Droop control, it's similarly, when the Q increase, it reduced the magnitude of this filter capacitor voltage. So in the fundamental frequency, actually its equivalent circuit is the voltage source, VO, behind this coupling reactance, L2. L1 cannot be considered as coupling reactance because this voltage loop already eliminates the dynamics here. It makes the filter capacitor voltage VO as the ideal voltage source. And it only has this L2 as its coupling reactance. So you can see for these two controls, even they are very similar, they have different equivalent circuit at the fundamental frequency. So if you still remember the first section's discussion, we know that the coupling reactance play a major role for the system stability, right? The larger coupling reactance results in a higher stability boundary. So for this section, I think this slide is probably the most important slide. This understanding is most important for this section. It's more important for the next small signal analysis and EMT simulations. So for the next slides, I will use some case study to explain this understanding. So first, let's still consider this very simple system, a two inverter system. We have two inverters supplying the load, and both inverters have this LCL filter, right? But in this case, we make this filter L1 much larger than L2. So you can see the L1 is much larger than L2. L1 is 6%, and the L1 is just L2 is just 1%. So, and actually for this microgrid, we can use both single and multi-loop controls, right? So at the left side for this small signal analysis, we have both inverters using the single loop control. And we can see that the system doesn't lose stability until the droop gain is higher than 9.2%. Now this is just because for this equivalent circuit, both L1 and L2 can be considered as its coupling reactance. So it has much larger coupling reactance here. But for the right side, if we have both inverters use this multi-loop droop control, because it's it has very small coupling reactance, only 1% for L2, so the system loses stability once the droop gain is larger than 2.3%. They look very similar, but their dynamic response are different because of this equivalent coupling reactance. So to better explain that, let's show some EMT and hardware in the loop testing results. For the same case, we have two inverters. They can either use single loop droop control or multi-loop droop control. For this case, we have 1% droop for both inverters, and we change the set point of one inverter to cause a small disturbance. And at the left side, we have both inverters using this single loop droop control. So you can see for their dynamic response, the system seems to be quite stable, not many oscillations. However, for the right side, if we have this two inverters using multi-loop droop control, we have the same disturbance, but we can see a much larger oscillation compared to the single loop droop case. Even they have the same droop gain, but they have very different dynamic response, right? This is just because they have different coupling reactance here. And also we perform the small signal stability analysis, and we obtain the small signal stability boundary. So you can see there on this boundary, if we both inverters use single loop droop control, because their coupling reactance is L1 plus L2 is 7%, so it is here, right? But if we use multi-loop droop control, because it has very small coupling reactance, you can see actually it's located here, right? It's already very close to this boundary. And for this case, if we increase the droop gain a little bit, we change the droop gain from 1% to 3%. You can see that at the left side, we can see a little bit more oscillation, but the system is still stable. But for the right side, for the multi-loop droop control, you can see that we see the system lose stability. This is because on this small signal stability boundary, we can see that when we increase the gains to 3%, the single loop droop control is still stable. It's within its stable region. But for multi-loop droop control, it exceeds the maximum droop gains at the unstable region. So that's why the system loses stability. So by the way, you can see here for the simulation, actually we put the PSCAD EMT simulation and the controller hardware in the loop simulation together. So you can see actually the results match very well. And also this EMT simulation compares very well with this small signal analysis. So this is the first case when we have L1 larger than L2. So you can see their dynamic responses are very different. So now let's look at the second case. For this case, we still use this two inverter system. But in this case, we reverse the value of L1 and L2. We want to make this L1 to be very small and this L2 to be very large. For like this case, L1 is 1%, L2 is 6%. So in this case, we can see that actually both single loop droop control and multi-loop droop control have very similar coupling reactance, right? Because one is for the single loop droop control, it doesn't change, it's still 7%. But for multi-loop droop control, because it has L2 as a coupling reactance, so its XL is 6%. So they are very similar, right? So we can see for the same case, but with L1 and L2 reversed, we can see that their dynamic response also become very similar. This is just because they have very similar coupling reactance. One is 7%, one is 6%. On this small signal stability boundary, they are very close to each other, right? And if we increase the gains to be 3%, again, you can see that they're still very similar. We can see some oscillation there. But for multi-loop Droop control, we can see the oscillations, it will be larger than the single loop Droop control. This is just because they still have a slightly smaller coupling reactance. And if we go further, if we want to test the small signal stability boundary, if we increase the Droop gain to 9%, so we can see that both of them are very close to the stability boundary, but the single loop Droop control is still stable, but very close to its boundary, so the the damping is really low here. But for the multi-loop Droop control, it's just lose stability because just outside is the stable region. So here I just want to provide some understanding of the difference of these two controls. So now let's consider an extreme case. This is not just a microgrid. This is about a multi-loop Droop controlled grid forming inverter connect to a very strong grid, maybe an infinite bus. And for this case, we do not have the L2 here. So in this case, I think I didn't run the simulation by myself, but I think you will probably have some problems if you run this simulation. This is because from this fundamental frequency analysis, we can see that there are equivalent circuits like you connect one voltage source directly to another voltage source, right? Based on the previous analysis. And the circuit law will prevent you from doing that because two voltage sources cannot be parallel. So you probably have to significantly reduce the gains to make this system work or use some virtual impedance control. So that's just some understanding on these two controls. And I hope this understanding can help people better understand the grid forming controls. So I'm not saying which control is bad or good, just want to understand them. And actually what I really want to say is that the better understanding of the control structure actually matters more than parameter tuning. Okay, so now let's move to the third section. So in the first two sections, we have discussed a lot about microgrid operation issues and the detailed power electronics controls. But here, what we really want to do is, when we have more and more such inverter-based resources connect to the bulk power system, how they really impact the system dynamic behavior. I think that's a very important question. And here I will talk a little bit about this background information. So we all know that many synchronous machines are retiring now. And meanwhile, more and more inverter-based resources are connected to both transmission and distribution levels. So we think because of this, the boundary between transmission and distribution system is blurring now, and the interaction between them need to be thoroughly investigated, especially regarding the system dynamic behavior and the stability. Meanwhile, because more and more inverters will be connected to the distribution level, like those distributed energy resources, we think maybe the future power system could have millions of these power electronics devices. So how do we understand the dynamic behaviors of such complex system with millions of power electronics devices connected at both transmission and distribution levels? So motivated by this question, so last year we conducted a short-term project funded by the lab internal funding to look at this issue. So what we did is that we used some DOE invested open source tools to develop an integrated transmission and distribution system, a co-simulation platform to look at how 10,000 inverters impact the system dynamic stability. So this slide shows actually what we did for that short-term project. So at the right side is the transmission system modeling. So we select this mini WAC system and model them in the open source tool called GridPack. So this is actually just a positive sequence simulator. It's actually very similar to PSSE and the PSLF. But this difference is that this GridPack actually support parallel computing, so it can be run on the supercomputer to speed up simulation. So at the transmission level, we use this mini WAC system. And at the left side, actually, we modeled this distribution system. Here we use this IE 8500 node test feeder as a distribution feeder. And then we added 550 inverters in this feeder. And these feeders can be either grid forming or grid following inverters. And these feeder, along with their inverters, are modeled in this distribution simulator called GridLab-D. So it's a simulator that can run the dynamic simulation of three-phase unbalanced distribution system. So I want to mention that this distribution system simulation is not just quasi-steady state simulation. It's a dynamic simulation for unbalanced distribution systems. And at the right side, we model the transmission system, and at the left side, we model this distribution system. And we use another open source tool called Helix to interconnect these two simulators. So what we did is that for this transmission system, it totally has 19 buses. So we replace 19 load bus. And for each load bus, we replace this load bus with 8500 node test feeder with 550 inverters. So that means for this integrated T&D system, we totally have more than 10,000 inverters connected at both distribution and the transmission levels. And the system size has maybe 160,000 nodes. So with this super complicated T&D system setup, we can look at how these inverters with different controls impact the system stability. So here I like to talk a little bit more about the system simulation setup. So for the transmission system, we have originally only had synchronous machines, but these synchronous machines can be replaced by either grid forming inverter or grid following inverters. And for the distribution system, we have 550 inverters. They can be either grid forming or grid following. However, there are too many different options. So here we made some assumption that we'll assume at the distribution level, we only have grid following inverters and working in the PQ control mode. But we do have their phasor lock loop model here. And for this system, the simulation time step is about 1 millisecond to 5 milliseconds. So we think this platform can do a lot of work, but for this project, we try to address two questions. So the first question is, if today we still the synchronous machine dominant system and we use this grid following inverters, how many grid following inverters can this synchronous machine dominant T&D system hold? So with this question, and we try to use this platform to run some simulation study. So you can see here, we just add different inverters in the system to study how these different penetration levels of the grid following inverters impact the system frequency stability. So as you can see here is the black dashed line is the base case, is a 100 machine based system. And once we gradually add the grid following inverter system, grid following inverters in the system, we can see that after the trip of 2 polyvoltage generation units, the frequency nadir gradually drops, right? As more grid following inverter in the system, the frequency nadir point just drops. This is reasonable, right? Because for this case, we didn't model the frequency support function that for that grid following inverters. So I want to mention that. However, even for that case, we find that if we go to 80% penetration of grid following inverters, we find that from the stability perspective, the system cannot run. It's not stable. We find that there are some 35 hertz oscillation in the system. So it doesn't run. So that means for this case, we can hold up to maybe 70% of grid following inverters. And then we know, okay, we need grid forming inverters maybe at higher penetration level. But the question would be, how many grid forming inverters are needed to maintain the system stability? So starting from this case, we know, okay, the system cannot work now. Maybe we need to add grid forming inverters. So for this case, we start with some grid following inverters in the system. As you can see here, for this 80% penetration case, if we replace maybe 4.7% grid following with grid forming, we can see that the frequency becomes stable now immediately. And if we continue to add the grid forming inverters in the system, maybe for this 90% case with 80.7% grid forming, the frequency stability is further improved. And finally, if we go to 100% IBR case with 12% grid forming, we can see the frequency nadir point is further improved. And basically, the dynamics looks disappeared. It's just like from one steady state to another steady state directly. If you compare this 100% case with this 100 machine case, you can see that the frequency response actually is better than this 100 machine case. This slide summarizes all the simulation cases we performed for this under this TND co-simulation platform. So you can see at the left side, we have all the cases with different total IBR penetration levels and different grid following inverters in the system. And the green one just represents a stable case, and the red one represents the unstable case. And based on this cable, all these cases, we obtained a stability boundary. You can see here at the horizontal axis is the total IBR penetration. And at the vertical axis is the share of grid forming inverters in the system. So we can see that if we only have grid following inverter in the system, maybe the system can go up to 70% penetration of grid following. And if we want to go further, we need more grid forming inverters in the system. As you can see, if we want to go to 100% penetration of IBRs, we need at least 12% grid forming. So I want to mention that this stability boundary is conducted based on this simple case, this TND case. And also this is mainly from the stability perspective. We already see that when we have more and more grid following inverter in the system frequency needle point dropped. So here I like to compare this case A and the case B a little bit. I think it's pretty interesting because case A means that if we only have grid following inverter in the system, we need 30% of synchronous machines to maintain the system stability. But for point B, that means if we have all the 100% IBR case, we only need 12% of grid forming to hold the rest 88% of grid following. So that means maybe grid forming inverter is more grid forming than synchronous machine because you only need 12% of grid forming to hold the rest of grid following inverters. So I want to mention that this is a short-term project. We have, as you can see, that we made a lot of assumptions, but hopefully, but fortunately, we have some funding support from the UNIFI consortium funded by this DOE solar and wind offices, and also some solar lab core project to continue to study this very important topic. Okay, so finally, I want to share some final thoughts and introduce some future work. So there are definitely a lot of questions need to be studied as we are moving towards a higher and higher penetration of inverter-based system. And I think I just want to highlight a few questions. So the first is from the control and operation perspective. I think one important thing for grid forming inverters is how should grid forming inverters should respond to short circuit faults? Because we make the grid forming inverters as a voltage source, and then it's have some problems with short circuit faults. But I want to mention that it's not just a current limiting issue. It's mainly about how different fault ride-through control of grid forming inverters impact a system transient stability with a mix of grid forming, grid following, and synchronous machines, and how that impact the power system protection. I think that's pretty important. And also another question is, here we just talk some little example inverter controls, but in the real system, it will have many different inverter controls produced by many different inverter manufacturers. And those controls are typically a black box. You can see the detailed controls there because they are proprietary technologies. So how should we develop those interoperability guidelines and functional requirements to guarantee the system stability and the reliability when we have a variety of IBR controls how can we make that work? That's from the control and the operation perspective. And from the modeling and simulation perspective, I think there's also some important questions need to be addressed. So for example, as I mentioned, in the future power system, there could be millions of power electronics devices. So what we did here is we take a look at about system behavior with 10,000 inverters. But how about the system with millions of power electronic devices? How we simulate them? Should we still use a full size model or aggregated model? I think we need to consider that. And also, the second question is, where is the boundary between the phasor-based simulation and the EMT simulation? Because for the first two sections, we use very detailed EMT models to study the detailed power electronics controls. But for the third section, we directly jump to the phasor-based simulation. to study the system with 10,000 inverters. But where is the boundary between them? So when we should use phasor-based simulation and when we should use EMT simulation for IBR-dominated power system, I think that need to be further studied. And also the third question is, I think it's also pretty interesting, is that, the older generation of power system engineers spend a lot of efforts on developing those synchronous machine dynamic models. Those models are very classic, but they are white box models. You can clearly see the detailed controls there, the models there. But for inverters, they are quite different. Because we need to fully respect the inverter manufacturer's proprietary technologies. So when the inverter manufacturers submit the models to the simulation engineers, those models are typically black box models. So we can not see all the details there. But does that mean if we are moving to a 100% inverter-based system, does that mean the power system engineers need to simulate a 100% black box model-based power system? Will that be a problem or not? I don't know, but I think it will be quite different from today's power system simulation. And how we make that work, I think that interoperability guidelines and functional requirements are probably the key for that. Okay, so this is today's presentation, and thank you very much. So I'm open to any questions now.
Thanks for the presentation, Wei. Diane, will we kill the recording?